Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is efficiency. Our objective is to introduce a common performance measurement known as efficiency. We'll learn to calculate efficiency for single-stage and multi-stage systems. This lecture operates under the presumption that viewers watch the Energy and Power lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. The real world isn't perfect. In the real world, things are hot and noisy, dogs vomit on your homework, and sometimes your lazy lab partner doesn't know what they're doing. The point is, losses will always occur. Due to the inevitable nature of losses, output can never be greater than input. Efficiency is a simple measure of the effectiveness of a system. Given a certain input, how much of this input is directed towards useful output, and which portion is misdirected towards losses. Efficiency is expressed mathematically as the ratio of usable output over given input times 100%. In practice, I tend to drop the percentage because it's cumbersome. Expressed as a ratio, efficiency is output over input. If you need to format the answer in percent, it's a simple matter of shifting the decimal point 2 places. 0.50 equals 50%, 65% is equal to 0.65, and so on. This three-variable expression can be expressed graphically with the use of a triangle, with output at the apex and efficiency and input at the base side by side. To calculate efficiency, divide output by input because output is over input. To calculate output, multiply input by efficiency because efficiency and input are side by side. Finally, to calculate input, divide output by efficiency because output is over efficiency. Given a certain portion of input is always misdirected towards losses, it would not be too bold to presume that useful output will always be less than input, never greater. If your calculations result in output greater than input, or efficiency of greater than 100%, you are doing it wrong and you need to perform a tactical retreat and reassess your data. Given that energy in a closed system can neither be created nor destroyed, but only changed in form, we can say that all incoming energy is converted into something else, and all systems are therefore 100% efficient. This is obviously not what we intend, and we must clearly delineate between what is considered useful output and what is considered a loss. Depending upon the application, one form of energy might be considered useful output, and another application, the same form, considered a loss. For example, heat is the intended useful output of a heater, whereas a motor, with the intended purpose of producing rotational mechanical power, any heat produced due to inefficiencies would be considered a loss. Let's try some simple illustrated examples of efficiency calculations. Consider a motor that consumes 2 kilowatts of real electrical power and produces 1.7 kilowatts of usable rotational mechanical power. Let's calculate the efficiency of this system. Efficiency is output over input. 1.7 kilowatts over 2 kilowatts yields 0.85. 0.85 expressed as a percentage yields an efficiency rating of 85%. This calculation also suggests that this motor is also 15% inefficient, meaning 15% of 2 kilowatts, or 300 watts, is directed towards losses, which might take the form of friction, noise, and/or heat. Consider a gearbox, known to be 95% efficient, that consumes 2 megawatts of mechanical power input. Let's calculate the usable rotational mechanical power output. Output is efficiency times input. 95% expressed as a ratio is 0.95. 0.95 times 2 megawatt yields a usable output of 1.9 megawatts. And the remaining 0.1 megawatts, or more appropriately 100 kilowatts, is directed towards losses. Check your work. Given losses always occur, output is less than input, as we'd expect. While we've got this example right in front of us, what happened to the missing 100 kilowatts? Has it disappeared? No. This power is going towards non-useful output, namely frictional losses, vibrations, heat, and/or sound. That's why it's so essential that a gearbox not include just the gears, bearings, shaft, seals, and housing, but also a means of lubricating and cooling these gears. This 100 kilowatts of losses has to go somewhere, and the film of oil coating the moving gears not only eliminates destructive metal-to-metal contact, but also transfers the heat away from the mating surfaces. It's for this reason you'll sometimes see a radiator or a heat exchanger used to cool the gearbox oil and rid itself of this heat so the oil doesn't thermally degrade and the gearbox continues to function properly. This also explains why gearboxes are built out of heavy metal rather than compressed cheese or origami. The housing must be sufficiently robust to absorb and dissipate the losses inherent in its operation. Finally, consider a hydraulic pump known to be 60% efficient that produces 1.2 horsepower usable hydraulic output. Let's calculate the mechanical power input in units of watts. Via unit conversion, 1.2 horsepower represents an output of 895.2 watts. Input is output over efficiency. 60% expressed as a ratio is 0.6. 895.2 over 0.6 yields a required input of 1,492 watts, or roughly 1.5 kilowatts. Check your work. Given losses always occur, input is greater than output, as we'd expect.